So I have prepared a Blackboard talk, which I assume is maybe easier to follow. So the topic will be on non-stationary quantum many-body dynamics. So perhaps this phrase non-stationary is not that familiar to you, or maybe it is. But so the motivation for studying this comes from, well, from various sources. One of which is an essay by Anderson from the 70s called More is Different. And I will quote where he says, I find that at least one phenomena seems to be identifiable and either universal or remarkably common, namely ordering or regularity, periodicity in the time domain. Okay, so this is what non-stationarity means. It means that you have a long time persistent non-trivial dynamics in many body systems. This is kind of opposite, well, not opposite, but it's almost opposite of ergodicity. So let me define ergodicity. I will be using, if you know, eigenstate thermalization hypothesis, I will be using in this sense. So ergodicity, weak ergodicity. I mean, if I take, say, some physical observable, let's call it O, okay, and then I take its long time average. Okay, sorry, sure. And I guess lower, I forgot. Yeah, okay. So weak ergodicity, so am I audible? Is it okay? Okay, so limit t goes to infinity, 1 over t, integral dt from 0 to t, O of t, right? So this is like the time average, should equal some canonical, whatever it means, ensemble average, yeah? This is weak ergodicity. Strong ergodicity is like this, but it holds without the averaging. So you just take the long time limit and you should recover the canonical ensemble. Okay, now the topic I will be discussing today is this, e to the I omega t. The question is what to put here. In other words, long time periodicity, yeah? Okay, so it is so clearly if you have non-stationarity, it is a type of what people call weak ergodicity breaking. And you generally do not expect a quantum many-body system or any many-body system to have such periodic dynamics in the long time limit. Indeed, statistical mechanics teaches us that this should not happen. But if we look at the world around us, it is quite common. I mean, it happens all the time, like Anderson writes. For instance, daily temperature variations throughout the year, yeah? So they're random, it's a random process, but there is a clear non-stationarity between summer and winter. So how to understand this? Well, in recent years, this topic of non-stationarity has been studied in various guises. I will try to show you this is more or less all of them are the same. They're all the same types of phenomena. And these are probably, you have heard many of these topics, so synchronization, limit cycles, or even quantum error correcting codes, quantum many-body scars, time crystals, and so on. And now I will show you there exist methods for doing exact analytical solutions in all such models, and at least for two classes of models. And this will be the topic of my lecture. So the first, and that will probably be what we'll do today, I will be studying finite systems. modeled by a time-independent Lindblad master equation. Lindblad. Secondly, more in line with the topic of this conference, I will move on to another class of exactly solvable models that we will compute this, yeah, and the expectation and this, the whole thing. And these are thermodynamically large, so thermodynamic. Large systems with crucially local interactions. And I'll define what I mean by that. Well, I hope you can see. So this will be also including isolated many-body systems, driven, so periodically driven in line with the topic, yeah, of the conf. Below, yeah. So isolated, driven in time, so time dependent, and dissipative, all of these. Yeah? So the crucial thing will be locality. Yeah? So although the frameworks I will discuss are very mathematical, my goal in these lectures, hopefully, so you can find them useful and maybe learn new methods to study problems you may be interested in. So I will go to trying to be maximally pedagogical and presenting everything in a way that you can actually use, yeah, to do exact solutions. Minimum rigor, yeah, so I will not prove anything. I will give you only, if where possible, some intuitive arguments why some statements are true. Okay, so let me tell you what I will not be discussing. So I will not be discussing classes of models that can be treated by other methods, such as semi-classical or mean field. So this I will not be discussing. So for that, I would recommend various works, some of them by people here in the audience. For instance, I have this paper that has a very nice way to treat limit cycles. PRA, I'll give you the exact references later on, okay? So that has very nice, discusses how to treat limit cycles in mean field models, for instance, yeah, or semi-classics. So why does mean field work anyway? Well, it works because of monogamy of entanglement, or if you will, concurrence. So there are certain bounds, and I'll give you a reference for that. So that's Osborne, Verstraete, PRL 26. There are bounds on this, and you can kind of show if the interactions are sufficiently long range, or if the local dimension of the number of local degrees of freedom in your system is big enough, mean field becomes exact. So I will be focusing on the opposite case. These are known as strongly interacting systems, or sometimes people also synonymous with many body systems. These are short range but strongly interacting models. So these are models that you cannot treat either mean field or h bar to 0. So this approach does not work for them. So we heard several talks on such models and various methods. Usually you try to do some perturbation type calculation analytically but it's difficult if you, especially if the model is very strongly correlated and so on. So these, unless you're probably familiar with what I'm talking about, but if you're not, these are kind of, in a sense, exotic models, but they are still very interesting. This is known as, in condensed matter, people call this quantum matter. So for instance, this includes high temperature superconductivity, quantum magnetism, topological orders, and so on. Yeah, so we would like to understand such models, and these models will be the topic of my talk. Other reasons we want to go beyond, say, semi-classics and mean field. Maybe we are interested in large systems, but still finite, yeah, that are difficult to treat numerically. Yeah? So for instance, this is the domain of quantum computing. Yeah? You have a big set of qubits that you cannot treat with classical numerics, but let's say you would like to still understand analytically what's going on. Okay. So my iPad is okay. Okay, so let us look at first this case. So finite systems, but still possibly large, modeled by a Lindblad master equation. So what is a Lindblad master equation? Well, so it is a toy. It's kind of, in certain cases, it becomes a very good approximation to a dissipative system, but mostly it's a theorist's toy model of a Markovian environment, where you have a system and you have a bat, and the bat has no memory, very fast, so on, etc., etc. I will not discuss how to derive it. I will just assume that it is modeling the system. And my system is described by density matrix rho. Again, I'm rho, which depends on time, and it satisfies this master equation that I will do second. So this is a super operator acting on the density matrix. I put hat, I mean super operator, yeah. And this super operator, aka the quantum Liouvillean or Lindbladian, is defined thusly. So this is the standard von Neumann part. L mu rho, L mu dagger, minus anti-commutator, L mu dagger, L mu rho. Okay, right. So this is the standard von Neumann part. This is the action modeling the environment. Okay, so formally, I can diagonalize this. This is a non-Hermitian matrix. It has distinct left and right eigenvectors, so I have to be careful about this. So let's diagonalize it formally in some set of eigenmodes. Okay, lambda k, rho k, and remember, yeah, distinct left and right, k, sigma k, sigma k. Yeah. These are bi-orthogonal, so this is true. Here I have defined that here I'm using an inner product that I will define in a second. And this inner product is usually taken to be the Hilbert-Schmidt inner product. So A, B, A, B, the definition is just trace A dagger B. This is the Hilbert-Schmidt inner product. It's an inner product. Okay, and now the solution to the dynamics can be just found by expanding density matrix and so on. So let's say now we want to find dynamics on observable. You can easily see that the solution is given in terms of this thing, sigma k, rho of 0, that's my initial density matrix, yeah? Okay, so in order to remember, the motivation is understanding this. So the eigenvalues of this quantum Liouvillean have interesting properties, at least for finite systems that we are studying now, finite systems. Back when we plot them on the complex plane, real part of lambda k, imaginary part of lambda k. So there is always one that's exactly 0, at least one. And all of the real parts are smaller or equal to 0. Okay. So this one is, if you put it here, you wait long enough, it's just gonna be stationary. It's not gonna change in time. These ones, if you wait long enough, they're negative real part, they'll decay. Yeah. But what we want to have non-stationarity is purely imaginary. Okay, and the question is, when is this true? When do we have these? And here I can give you a full answer for this finite systems, yeah, for finite systems, finite dimensional Hilbert spaces, to be more precise. And okay, so this is my paper. Suppose 2022. Okay. So theorem 1. Let's begin. Theorem 1. The following condition is necessary and sufficient for the existence of an eigenstate rho with purely imaginary eigenvalue I lambda. So rho I lambda, yeah. Now I took the I out, and lambda is real. We have rho, so this is equivalent, yeah. Purely imaginary eigenvalue, these conditions, purely imaginary eigenvalue, necessary and sufficient. Is A times rho infinity. Rho infinity is a special, this is the state with exactly eigenvalue 0, also known as the non-equilibrium stationary steady state or NES or stationary state, blah, blah. And A is an operator fulfilling these conditions. L mu A, rho infinity equals 0, and minus I HA minus sum over Lindblad's L mu dagger A L mu rho infinity equals I lambda A rho infinity. Okay. So yeah, it doesn't this okay, this condition looks kind of okay. This one is a bit complicated. So what's the point of this? Well, the point is twofold. First, if you can identify, let's say you find a system that has, you think it may have a purely imaginary eigenvalue for some reason. Let's say you see persistent oscillations, and now you say, okay, can I solve for this? And yes, if you can find the A and the rho infinity. So you can say, okay, this is complicated, this is not help me, yeah? But it turns out, in many cases, numerous cases, in fact, almost all natural cases, you can easily identify this A via some symmetry consideration. Now, in that light, I give you theorem 2. If there exists a stationary state, so some station, not necessarily one, but some stationary state, let's call it now rho tilde, which is in math-phys parlance a fateful, but essentially means that it's invertible. So it has no zero eigenvalues. Okay. For example, if you're in an equilibrium situation, this is such a state. Then there exists a purely imaginary eigenvalues if and only if rho, that is the eigenmode or eigenvector of the quantum Liouvillean with the purely imaginary eigenvalue, is expressed in this form. Actually, it's a set of them, Nm, A to the n, rho infinity, A dagger to the M, where A we now call a strong dynamical symmetry. At least I called it before I knew the name dynamical symmetry was taken for something else, but what can you do? Satisfying these much simpler conditions is now I'm going to call it omega now. Or should I keep it? Yeah, let's keep it. Let's keep it lambda for now at least. Okay. No, wait, I don't want to keep. I'm going to keep it omega. And these. U dagger A equals 0 for all mu. Then the purely imaginary eigenvalues lambda are of the form omega times n minus m. You can give it the same. You can give the same equivalent for the left eigenmodes. So now note, if you know you have such an invertible state for some reason, let's say your map is unital. So for instance, unital map is such that these are, for instance, Hermitian. L mu's are Hermitian. Then you know your steady state isn't. You have a steady state that is invertible, and you see oscillations. Then the question is, okay, can I solve? And then I can solve using, and I know it must be due to this structure. Yeah. And moreover, if you identify such a structure, you immediately get the full solution, okay, for the long time dynamics. This is like, if you will, such a raising operator on the imaginary axis. Now, okay, so it's okay, but this is still, you know, it's not easy. I don't know this. Well, it will turn out, and we'll see in examples, that these structures usually come from some algebraic, some generalized sort of symmetry type condition. Yeah, if you can guess them, kind of. I'll try to show you how. But first note, let's do a sanity check. Let's consider what happens if I did not have a, if I had a closed system. So if I had a closed system, I know that this is a stationary state. Yeah, I plug in and it's 0, so it's stationary. So then what are these things? What are these A's? Well, it turns out here I assume you have at least, you have one A. You can have more than one A. Yeah? You can have an infinite number of A. Well, not infinite because we're treating finite systems, but you can have as many A's as you like. And indeed, for a closed system, this A takes a very simple form. Well, not simple, but formally looks simple. And these A's are of the type A is psi K, psi, I don't know, J, psi J, where these are just eigenstates of the Hamiltonian, yeah? So you see kind of, usually this won't help us do solutions, but it will turn out, actually, once you put the dissipation in, most of these things will just go away and there will be just a few A left, yeah? So this helps you, yeah? It kind of dissipation makes the problem easier to solve. Okay. Okay, so what to do with this? Well, one thing we can do with it is, it turns out, and these people have studied before in more general, well, not more general, but have studied the structure of these purely imaginary eigenvalues or the corresponding eigenstates. And it turns out that sometimes these states can host quantum coherences. Okay, let's say you have a quantum computer. You want to do a quantum gate. A quantum gate you can model via some e to the I, some Hamiltonian, yeah? But you have noise because you live in the real world, okay? You have noise, and what can you do? Well, you say, okay, I can do the gate anyway, and then you'll find that if you insist on doing this, you cannot do many gates without completely ruining your calculation. But there are tricks. So there are tricks, and these purely imaginary eigenvalues can help you. They can host something called decoherence-free subspace. So it is a set, decoherence-free subspace is a set of pure states that, well, you can write the corresponding eigenmodes in this way, yeah? So this is a decoherence-free subspace. So, and then you're okay, you're in a pure state. You can do quantum computation. If you're in a decoherence-free subspace, there are generalizations of this noiseless subsystem. Where your state is now of the form, your purely imaginary eigenvalue of this form. Tensor some mixed state, but such that this part is still pure. So you can still do quantum computation on some subsystem. This may not be physically subsystem in space. It can be, it's a subsystem of the Hilbert space. Yeah? And there are more general things who call multi-block structures, who have, from a quantum computation perspective, are more complicated. So there are direct sums of these noiseless subsystems. They're, whether or not they are useful for quantum computation, it's kind of tricky. But okay, this has been studied a lot by people like, I don't know, I can give you Baumgartner, Naunhofer, I'll give you the references later. Viola, Lidar, Zanardi, and so on. Okay, so that's one thing you can do with them. Note, a quantum computer clearly is a non-stationary thing. You want to do, well, at least while you're doing quantum computation, you don't want the thing to equilibrate or become stationary. Yeah, then you're no longer, then you can by definition no longer perform the computation. Okay, so that's one thing. Another thing will be quantum synchronization. So we are now moving to another topic. Half an hour, okay. Good. So what is quantum synchronization? I wanted to show a video, but I don't want to complicate technical issues too much, so let me draw you a picture. So classical synchronization, you can, if you search on YouTube synchronization, you'll find such things. Let's say you have some bunch of pendulums, and you initialize, you connect them, and you initialize them at various positions, and then you let them swing. So at first, you'll see that they swing like out of phase completely, but if you wait long enough, they'll lock into phase. And they'll continue swinging, yeah? So it's clearly non-stationary, they're swinging forever, well, not forever, but for a long time. And yeah, so this is quite, synchronization is again a phenomenon that happens a lot in our brain. Fireflies do it, etc., etc. And quantum synchronization is an interesting topic also for quantum systems. And using this, I can give you the full solution to quantum synchronization, yeah? At least for finite systems. So if you have a finite system and you reach the high, is it synchronized? Will it synchronize? Well, if you define it in such a way, namely that you have some quantum system, here are some thingies, yeah, they live somehow whatever you like, it's finite, bunch of thingies, subsystems, let's say J and K, yeah? And then you say, okay, I say I have quantum synchronization if the expectation value of observables on subsystem J equals that on subsystem K if I wait long enough, okay? And I call this is the definition I use, I call it robust synchronization. Okay, so when let's say, so one thing we would like is, of course, to, like classical synchronization, we want the thing to be non-stationary, but we also want it to lock in, all the subsystems to lock into phase. So the following is sufficient to get such thing. Let's look at the simpler case, theorem 2. There is a condition also for theorem 1. Well, let's look at theorem 2. In my experience, this is more generic. So, okay, now we're back. I don't know why I crossed this out. Sorry. Now we're back to generic, in generality, open system. Yeah. Okay. So there exists at least one A fulfilling the conditions of this theorem. And moreover, all A that satisfy these conditions, all the operators A, commute with a permutation operator exchanging system K and J. Okay, so for all the A, for all A, and that's it. So if you have of all your A satisfy this, so it commutes with the permutation and purely imaginary, of course, yeah, they're A by definition. J and K, if you wait long enough, are guaranteed to be quantum synchronized. Yeah. Okay. All right. Where am I now? With time, 20 minutes. Okay, so another thing I wanted to discuss is time crystal. So we had a nice talk by Subjahid on time crystals and dissipation. So in periodically driven systems. So for the moment, I will maybe focus on time independent systems, but let's see, what's the best way now with the slides? Let's see how we do with time. Okay, so maybe I will ask now if you could please lower the screen so I can show something on the slides. And then we'll see how we do with time. Maybe I'll leave longer for questions this time. If not, I'll, let's see. So please, yes. Okay. Or maybe, are there any questions at this point?
So what if we have phase synchronization, but not the amplitude synchronization?
Yeah, then you need to just redefine permutation operator.
Okay. Phase permutation operator.
Yeah, redefine. You can, this is the simplest case. More exotic things, you can redefine permutation so that the amplitude, it also switches the amplitudes in some ratio, etc. Okay. Yeah, that you like. I mean, you can see this from the structure of DA. If DA is like this, okay. Right. Okay. So here I am. Yes. Share the screen. Okay. So here is synchronization. I will not give you. It's some spin one model. You can find it in this paper. The exact details are. I don't want to give you because maybe it will just be too. I don't want to stray too much from the really main idea. I'll give you an example later of something else, but this system can be closed and can be open. If it's closed, right, as I wrote on the board, you have a ton of A's, all of the combinations of the eigenstates of the Hamiltonian. If it's open, there is exactly one A, only one. And now this is how expectation value of some observable looks if the system has interaction, so beyond quadratic and dissipation. So here you have three sites. You can see that the long time dynamics is persistent and it synchronizes into phase and in phase and frequency and amplitude. So if we switch off interactions, more A's appear. So we still have dissipation, but we have more than one A. So there are persistent oscillations, but there is no synchronization. Yeah. Likewise, if we turn off the dissipation thing, then you get really a large number of A's with various frequency, eigenfrequencies of the Hamiltonian. It's just a mess. Yeah. Okay. So so since as I said, these are necessary and sufficient conditions. This is why I claim people kind of see synchronization in dissipative systems. You need dissipation to get rid of all of these frequencies. Yeah. Okay. So another thing I wanted to discuss, and Subcha, he discussed a very nice talk on Floquet dissipative time crystals. I want to discuss now type of time crystal. First, let me say what a time crystal is. So the idea was, well, it comes in two forms, or well, more than two, but two general forms. One is one people call continuous time crystal, where you have a many body system or something that you think should thermalize, but rather you see it displays persistent oscillations at one period. So this is like a crystal in space that has, you know, instead of the full space translation symmetry, it's broken into a lower one to a discrete one. Much like this is in time, hence the name time crystal. There's also something called discrete or Floquet time crystal, which you have an external periodic drive. And then you break this drive into, by, say, period doubling, yeah? The period of the drive, so it gets like period doubling. Let me give you now an example of a dissipative continuous time crystal that I define in a certain way. So this is one, and this is how you can also identify A's. This is a very simple case, at least from this perspective. So this is a system that satisfies these conditions. So it's a d-dimensional Hubbard model on a bipartite lattice. It has, I added, here you have, what do you call, you have a maybe, here. Okay. So, yeah, so here you have fermions hopping around. They have two spins, two spin states, blah, blah. Here you have on-site interaction, and here's some arbitrary electric fields or chemical potentials, if you will, and there is a constant magnetic field. So if I turn off this, I just have a full SU2 symmetry, which is just the spin symmetry, so it's very simple. But if I turn it off, then I get a trivial dynamical symmetry on the system, which is this total spin raising operator, okay? But let's say now, okay, so because the Hubbard model has two SU2 symmetries, anything in the other symmetry sector, which is eta pairing, incidentally, will commute with S plus. Okay, so any combination of local operator or non-local operator from the other symmetry sector will commute. For instance, this will commute when you have a type of dephasing, on-site dephasing in just particle number. And therefore, the conditions of theorem 2 are fulfilled. You have purely imaginary eigenvalues, and then you get oscillation. Let me give you the main idea here. So, okay, here is a simple example. So we look at some magnetic field on some site. We do what kind of a type of quench. We do, we change start in some ground state, change the interaction strength, and switch on some disorder in the field, yeah? This is not MBL, it's something else, but we switch on disorder to make the distinction more dramatic. Anyway, so the closed system, as you can see, kind of really isn't anything you would call a time crystal. That's the black line. But the open system, the one that has dissipation, is nice, displays nice, robust periodic oscillations at one frequency. So it's kind of, I mean, I like this analogy. It's kind of like you have, let's say, you have a many body system. That's your closed system. It has some friction, like this pendulum, and so it stops, yeah, or at least, you know, jiggles randomly. If you had just normal dissipation, you would it would stop swinging even faster. But here we have found some dynamically symmetric source of dissipation that allows it to that cancels the original one, kind of. Yeah. So yeah, this is a continuous dissipative time crystal. This is how I define it. I will not discuss Floquet dissipative time crystals. Yes. How do you define this? Can you be more precise? Can you define breaking here? This is out of equilibrium. No, but I mean, what in what? I mean, depends in what sense. Yeah. I have broken explicitly the SU2. Yeah, it's explicit. It's a type of explicit breaking. It's not spontaneous. So I have that. By introducing the field.
I guess what's confusing me is, in the discrete time crystals, Floquet time crystals, you have a notion of a spatio-temporal symmetry breaking.
Yes.
And I'm just wondering what the difference is to what you're showing here.
It's different in the sense that the definition I'm using is different. So I would say dissipation. I call it dissipation induced because dissipation induced. If you have no dissipation, you have no time crystal. So that. Yes.
That is broken. Right. Right. Exactly.
Yeah, exactly.
So in that sense, there's no spatial symmetry that goes in. Exactly. Yeah.
Yes.
Okay.
You mean order in space? No, I mean, but you can. This is well, okay. It's a bit tricky because usually in equilibrium you define order via correlation function, and here you have to do it. You have to take the correlation with respect to some state. And now in this case, because the time translation, with respect to which state, yeah, do you want? So this is a highly non-ergodic situation. So if I take it with respect to a purely imaginary sum of these, yeah, and then I look at the correlation, then I will get to order. But if I look with respect to some stationary state, I may not. So it's not very well defined, let's say. Yeah. Spatial order in this case. We're out of equilibrium here. I can put it in by hand, let's say. So, but the question is, will it appear from any natural enough eigenstate? And the answer is no. Natural enough initial state, and the answer is no. But this follows from Lieb-Robinson anyway. Is that kind of sufficiently okay answer? Okay, so well, I'm really ahead of time here. Okay, blah blah. Okay, these are the references. So since I'm so ahead of time, I'm gonna okay, we can maybe move to questions, but let me just give you a preview of tomorrow's lecture first. So I'm very sorry, and I would like to ask the gentlemen, please, if they could raise the screen again so I can go back to the board. So 5 minutes just to give you a preview of what we're going to talk about. Yeah, but I think if the Zoom won't see it, they have to really move the thing, right? We have to raise it to so you can put the board on Zoom if I understand correctly. Yeah. Well, anyway, let me start. I think it's okay. So next time, tomorrow, I'll talk about thermodynamically large systems. These are finite systems. Yeah. Now we do thermodynamically large. So yeah, maybe just okay, well, maybe just a recap. So before I discuss that, let's just do a recap of what I did today. So let's say you have non-stationarity in an open Markovian Lindblad type situation in a finite system. I say You can do exact solutions, provided you can identify this A via some dynamical symmetry, via some considerations, for instance, breaking explicitly some sort of non-abelian symmetry you have, and so on. Yeah. But what about thermodynamically large systems? You say, okay, so finite systems, you come from a stat-mech background, even if they're open, you think, okay, maybe that's not that interesting. Well, for infinitely large systems, I cannot, unfortunately, give you full exact solutions in all generality. I can, however, give it for local interacting systems. Local interacting systems means that, well, I'll discuss what it means. But first, let me discuss what we expect will happen in a many-body thermodynamic large system. And this is known as eigenstate thermalization hypothesis, which you probably heard in two forms, weak. So, which is this. Ooh, this is the advantage of using the board, right? So I can just weak. So it says this, and this is just, say, generalized, including integrability. This is just a trace e to the minus beta h is my Hamiltonian, plus possibly some set of chemical potentials here over z. Yeah, I guess. Yes, no, yes. Oh, close, no, close, yeah. And O. Yeah. So I just take expectation value of my O with respect to this state, and these Q's are conserved charges. Yeah. So this is what the weak ETH says. This is weak ETH. I'll tell you how to prove this. Yeah. Strong ETH holds, at least in local interacting systems. Strong ETH holds without this. So you just take no average, you just take long time limit, and this same thing should hold. It's a strong ETH has known. If you define it precisely enough, you can probably find a counterexample, and the various now are known, even beyond so-called generalized ETH, which includes integrable models, quantum many-body scars, and so on. There are known counterexamples. But tomorrow I'll show you how to prove weak ETH in local interacting systems and how to solve for this. Yeah. So I will give you essentially, I will tell you what you need to put in here. Okay, now we'll be, okay, now we're at finite frequency. I'll tell you how you need to change this and what to put in here so that you get the solution. Yeah. And we'll kind of try to figure it out together in a natural sort of way. Yeah. Okay. So, okay, 6 minutes. And I will do so for, okay, so I will do very, very mild assumptions. So local interactions. So this means, let's say I have a Hamiltonian that I can write as a sum of local terms. If you like, let's draw a picture. So my Hamiltonian is not necessarily nearest neighbor, but you know, the interactions are of finite range, you know. And for initial states, so of course weak ETH, maybe forgot to say, this expectation value is taken with respect to some initial state. Yeah. See Heisenberg now. Some initial state, yeah. Okay, so for what kind of initial state can I treat? Well, I can treat initial states that have no long range order in space or not too long range order. So let's say this size 0. Let me. When X and Y are much big, yeah. So they kind of just, the correlator just, you know, factorizes. There's no long range order, the connected correlation. And what kind of observables? Well, local observables. What does local observable mean? Well, you have your many body system. I will treat d-dimensional models on finite, on infinite lattices, yeah, in d dimensions. I again emphasize this has nothing to do with integrability. This is the thing works for all the even chaotic models. So I want to study local observables, which means that my observable lives on some finite connected region, yeah, of the system that I label with X, yeah. So X, so when these two local observables are very far apart, there is no correlation. Okay, so this is the setup I will be pursuing. And indeed, okay, oh, I have 3 more minutes. Okay. Indeed, this is you have to do some sort of like additional things on top of this. Why? Well, because if I take an observable, let's say I have two, my observable is just whatever I like. So this plus HC, and these are two eigenstates of my Hamiltonian. I plug it in. So of course, and if I take a state that's a superposition of these two eigenstates, this you're going to get oscillations forever, yeah. Okay, you can easily violate any sort of ETH in this way, yeah. If you take two eigenstates that are very far apart in energy, you do whatever you like, yeah. So I need these conditions to actually prove this, yeah, and generalize it to finite frequency. So it's like kind of finite frequency ETH. Okay, that's it for today. Tomorrow we'll do this, yeah, and I'll tell you how to do scars, so solve for scars, yeah, as an example. Okay, thank you.
I have a question.
Sorry. Can you just put it down so the people can see the references again? So they know what I want. Yes.
I think the screen is going to cover the figure I was going to ask about. For the
Oh,
synchronization theorem,
yes.
you have a permutation operator that appears.
Yes.
PJK.
Yes.
And I could see how that would be natural for 3 oscillators, say, but for the coupled oscillators you drew, it's not obvious to me that a permutation symmetry is going to be very relevant to that diagram to the left. Like, in other words, I would have thought that something that required permutation symmetry would be like an all-to-all coupled model. So, like, if I just
no, not permutation symmetry of the Hamiltonian of the A.
Okay, but it's natural to have a permutation symmetry of the A, even if the underlying system does not have anything like a permutation symmetry?
For sure. Yes, it is. This is indeed possible. So the example I gave with the Hubbard model that has the disordered field, the underlying model has no permutation symmetry. It's a d-dimensional model anyway, no lattice. The A is just the sum of all the spin raising operators. The sum of all the spin raising operators, the A itself, is completely permutational invariant. So it will synchronize, yes.
Okay.
Yeah.
Do you have any intuition for when this A exists? Like what kind of systems you might expect to have an A?
Yes. So the easiest thing is if you have an non-abelian symmetry and you explicitly break it. Well, like I did by introducing a field, then you will get an A by construction. This kind of trivial. So there are more complicated cases that it's still an open question, let's say, when this happened. It's kind of, symmetries, I would say, intuitively we understand, but dynamical symmetries are not that well understood. I can give you exotic examples ranging. I can just give you sets of examples. Unfortunately, there's no intuition. I can give you something from exotic quantum group structures all the way to some things that have come from fermionic modes or something.
Time for a few other questions? Yeah.
So if you have a dynamical symmetry for the trajectories, two things can happen. Either all the trajectories oscillate with the same frequency, or, and this is if these eigenmodes are the coherence-free subspaces. So then you just have unitary dynamics. This is what it's saying, yeah. If they're not, if they have some entropy content, if they're a noiseless subsystem or multi-block, or actually you mean multi-block for sure. I'm not sure about noiseless systems, but for multi-block, then it's kind of interesting, and it's kind of related to what I said between this summer and winter. You have it's a random process that looks non-stationary, it's a random stochastic process. That's how your trajectories look like, but they have a seasonality, yeah, right? Like they look kind of like temperatures throughout the year. Yeah? That's kind of that frequency, yeah. So indeed, yes, it has implications.
Your examples seem to have only oscillations with a single frequency.
Yes, I wanted synchronization. Yes.
But like, for instance, classical systems, you also have chaotic synchronization.
Ooh.
Is that not possible?
There, and that ties into another example. Yes, you can have this. Yes, and I can give you a reference for it. There it comes about. It's a localized. In that case, that case will probably not synchronize. So it's well, I can give you the example of so it's a spin 1/2 model that lives, I call it spin lace. Like this, la 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 la. Yeah, so these are spin 1/2s, and then you have localized A's here at various frequencies, and then you can, if you study, right, we did this with Archak. If you study the dynamics, they will look. It kind of looks like some sort of attractor-like behavior. It's more complicated, but yes, indeed.
Thank you.
Thank you.
Maybe time for one last question, if there is one.
Yeah, I had a question that was a little bit similar to Joel's, actually. I was just wondering if there was any kind of intuition for a kind of constructive way to form your operator A. So you gave some kind of intuitive examples based on closed systems, and you have some hard constraints on what this operator has to satisfy.
Yes. Yeah, so yeah, I would like to have this. If, like I said, if you take any non-abelian symmetry, you take any H, it has some non-abelian symmetries, yeah? Let's say it has two non-abelian symmetries, like the Hubbard has SU2 times SU2. And then let's say you decide okay, I'm going to break one of the symmetries explicitly by adding a field, okay? Yeah, so now I break, and now I get, so my H commutator A will be omega A, and A's will be just strictly speaking, it's called the root of the algebra, yeah? And then that's what the A's will be, like S plus total spin raising, for instance. And then if I pick my Lindblads to be something that's kind of, that lives in the other thing, then you're fine. Then these are the conditions, and you have this. Yeah? So any model of this type will have this. That's the most constructive thing I know of for now, yeah. There are other examples that go beyond this, but they're kind of in their own class, yeah. But this is very general and kind of simple.
All right, I think we better break, but let's first thank the speaker again.
Thank you.